So Kalpana will start.
Okay.
Namaskar.
Okay.
And a very good morning, distinguished guests, resource speakers, esteemed participants, ladies and gentlemen. Hope I am audible to all. My name is Kalpana Adhikari from Committee for International Commission on Large Dams India, INCODE. On behalf of INCODE, we extend a hearty welcome to the dignitaries and resource speaker, including ICOL President Mr. Michael Roger, Vice President INCODE Committee on Concrete Dam, Dr. Quentin Shah, and who is the resource behind this workshop and helped INCODE in mobilizing of world-renowned experts to this workshop. Dr. Malcolm Dustin, longest serving member on the ICOL Committee on Concrete Dams and chairman of the committee that drafted ICOL Bulletin 109. Co-founder of ICOL Young Engineers Forum, Dr. Marco Conrad, and other world-renowned experts, Mr. Francisco Ortega, Mr. Christopher Hicks, Mr. Rafael Aldico, Mr. Tim Dolan. Hope I have pronounced the names correctly with my accent. I also welcome ICOL Vice President and President INCODE, Mr. D.K. Sharma, Vice President INCODE and Member DNR, Central Water Commission, Government of India, Dr. R.K. Gupta, Secretary General, Mr. Aditya Kumar Dinkar, Treasurer, Dr. G.B. Patel, our esteemed guests and other dignitaries from India and abroad. Kindly excuse if we missed name of some of eminent ICOL family members. We convey our sincere thanks to all professionals for their time and presence for today's workshop on the topic applicability and feasibility of roller compacted concrete dams. Ladies and gentlemen, RCC dams have the virtue of saving a great deal of concrete, building quickly, bringing project costs down, early completion of the project, and so on and so forth. Hence, this technique of constructing dams has quickly spread and applied since it came out. Today, there are more than 700 RCC dams in more than 40 countries where great successful experiences have been observed. India has also constructed few RCC dams such as Ghatkar Pump Storage, Middle Vetrana in the state of Maharashtra of high range of 100-110 meter, Testa Low Dam 4 of NHPC. Now the 280 meter dam in northeast part of India, Divang, is being done as RCC dam. Sahapur Kandi, 55.5 meter height in Punjab, Lakhwan Dam in Uttarakhand, and Sanwal Kot 192 meter height in Jammu and Kashmir. There appears a need to propagate about RCC technology, including planning, design, construction, equipment, cost aspects, O&M, etc., specifically highlighting the scope for utilization of bulk quality of fly ash of about 225 million tons being produced annually in thermal power station in the country. Now I invite Mr. D.K. Sharma, President INCOL, Vice President ICOL, for the welcome address and to share his thoughts on the topic of the workshop. Over to you, sir.
Thank you, Kalpana. President ICOL, Mr. Michael Rogers, Vice President INCOL, Dr. R.K. Gupta, Mr. A.K. Dinkar, Secretary General INCOL, Mr. G.P. Patel, Director CBIP, Director Water Resources CBIP. Resource speakers of this 3 days workshop, Dr. Malcolm Dunstan, Mr. Quentin Shah, Francisco Ortega, Rafael Ivanez de Aldecoa, Marco Conrad, Tim Dolan, Chris Hicks, delegates from all parts of India, ladies and gentlemen. On behalf of the Committee of International Commission of Large Dams, India, also known as INCOLD, and the International Commission of Large Dams, ICOLD. It's my proud privilege to welcome you all to this virtual workshop on applicability and feasibility of roller compacted concrete dams, scheduled to be held today, tomorrow, and day after. Mr. Quentin Shah is the driving force behind this workshop because we are really grateful to him to have mobilized all the speakers for this workshop. It is our great privilege to have these world-renowned speakers for the workshop because India has made a beginning in roller compacted concrete dams, but we are a long way to go to catch up with the rest of the world. Purpose of this virtual workshop is to make available to all engineers about the current practices in the use of roller compacted concrete dams, roller compacted concrete for dams. There has been a continuous and rapid development in this field, and although the technology has now matured, advances still continue to be made. There are nevertheless different concepts of design and construction in use in various countries. This workshop will provide a comprehensive review of the state of the art of the design and construction of RCC dams. Various design concepts will be presented ranging from those with wide application to those developed for very site-specific conditions, available materials, and foundation conditions. Examples range from the sophisticated to simple applications. As in the case generally in the design of a dam, design and construction concepts should be selected with regard to local conditions and performance requirements of the dam in terms of cost and efficiency. As you are aware, the term roller compacted concrete dam concrete describes concrete used in construction process which combines the economical and rapid placing techniques used for fill dams with the strength and durability of concrete. RCC is concrete with no slump consistency and its unhardened state that is transported, placed, and compacted using fill dam construction equipment. The properties of hardened RCC are similar to those traditionally placed concrete. Placement of RCC is in horizontal layers similar to the construction techniques of earth and rock fill dams. Using this construction procedure, RCC dams can be raised at a rate closer to 30 meters per month or in certain cases even more. Number of joints between the relatively thin layers and the related quality control can have a large influence on the overall stability of the dam in terms of uplift water pressure, tensile and shear cohesion strength at the joints between the layers. RCC dam designs use two main design approaches. The overall approach, which relies on the dam watertightness, although the quality and proper treatment of each lift of the joint is essential. The separate approach, which relies on an independent impervious barrier, which is usually placed on the upstream face of the dam in a similar manner to that with concrete faced rock-fill dam. The extreme equipment of this is the hard fill or the cemented sand and gravel dam, which because of larger cross section is less reliant to tensile and cohesive strength. Apart from these design approaches, which are related to water barrier, various other approaches are encountered internationally, particularly for small-sized and medium-sized RCC dams. In addition, there are approaches which are essentially specific to one country, some of which are described in their national documents. For example, Japan is the principal exponent of RCC dam method. Similarly, Brazil has developed high fines RCC that are suitable to the conditions in that country where there are little or no mineral admixtures economically available because of long distances and where dynamic loading is low and thus the strength requirement of RCC are correspondingly low. In several cases, alternative designs using RCC construction methodologies proposed by contractors during the bidding process have been found to be more economical than the originally specified Rockville and arch dam designs. This illustrates the benefit of inputs from construction companies during the design process for RCC dams. The majority of RCC contain mineral admixtures, mainly fly ash, as an active constituent of the concrete, and one of the major advances in concrete technology brought about by the development of RCC dam has been the greater understanding of the performance of mineral admixtures in concrete. There are exceptions, such as part of Brazil where admixtures are not generally available. RCC dams are being used for dam rehabilitation and raising as well. ICOL President Michael Rogers will talk tomorrow about rehabilitation and raising of Gross Dam in Denver. During the coming 3 days, world-renowned experts would talk to you about world trends in RCC, introduction to ICOL Bulletin 177, RCC dam design, materials and mix proportioning, dam construction, quality control, performance of the RCC dams, and construction systems and automation of RCC dams. Well, gentlemen, I wish good luck for success of this virtual workshop, which is very vital for the growth of construction of RCC dams in India. I once again, I'm thankful to all international experts who have agreed to our request to deliver lecture to Indian engineers during this virtual workshop. Thank you. Thank you very much.
Thank you, sir, for your thoughtful address by sharing the important aspects of RCC dam, which will set the tone of deliberation for this session. Thank you. Now we have today's first resource speaker, Dr. Malcolm Dustin's presentation on world trends in RCC. Let me introduce briefly about the speaker. Dr. Malcolm Dustin obtained his first degree from Birmingham University and his PhD from Surrey University, both in UK. He is the chairman of Malcolm Dustin and Associates. He has been involved with more than 140 RCC dams in 53 different countries during the past 40 years. He is the longest serving member on the ICOL Concrete Committee and was chairman of the committee that drafted ICOL Bulletin 109, Concrete Dams, Control and Treatment of Crack, and 126, Roller Compact Concrete Dams, State of the Art and Case Histories. He is the author of many papers and maintains a database of all the RCC dams in the world, a summary of which is published annually in the Hydropower and Dam World Atlas and Industry Guide. At the Ottawa ICOL 2019 annual meeting, he was awarded as honorary membership of ICOL. Now I request my colleague to play the recorded presentation received from Dr. Malcolm Dustin. May I request the IT team to please play the recorded message, recorded presentation?
Good morning, ladies and gentlemen. I'll be talking about world trends in RCC dam design and construction, how things have changed over the last decade or so, and the position with RCC dams at this present moment. I'll first look at an RCC dam database that we've been maintaining for about 30 years. Secondly, I'll look at RCC dams around the world, then look at the design philosophies of RCC dams, the cementitious materials used in RCC dams, the highest, largest and fastest RCC dams, and then the speed of construction, which is the main advantage of RCC dams. And I'll look at the 4 completed RCC dams in India, and finally draw some conclusions. As mentioned, we've been maintaining a database of all the RCC dams in the world for nearly 30 years, and a summary table of that database is published annually in the World Atlas of Hydropower and Dams, and this is the first page of the latest version. However, you can search for any RCC dam with the searchable database on our website. Very simple website to remember, www.rccdams.com. You can search for dams individually, by country, by height, by type of SCM, that's supplementary cementary material, and within ranges. You can then look at that in many different ways, one of which is a map view, in this particular case showing all the RCC dams in the world for which we have coordinates. And these are the 4 RCC dams which have been completed in India to date, 3 of them in Maharashtra and 1 in West Bengal, and I will talk about these later. These are the 3 in Maharashtra, Middle Vatana, the 2 dams at Gatgar, the upper dam and the lower dam. Here is the Gatgar project, which I'll be talking about later. And here is the Gatgar lower dam. Now the RCC dams around the world. I'll first look at the number of RCC dams and then the distribution of those dams around the world. At the moment, there are 956 known 15-meter plus high RCC dams, for which we have details. Of those, 886 are complete with an RCC volume of 370 million cubic meters, and a further 70 are under construction with another RCC volume of 32.5 million cubic meters. In other words, there are over 400 million cubic meters of RCC in dams, either complete or under construction. Of those dams, 805 are over 30 meters high, and of those, 741 are complete with a volume of 355 million cubic meters, and a further 64 are under construction with an RCC volume of 30 million cubic meters. 11.6% of the 30-meter plus high completed dams are arch or arch gravity dams. If we now look at the same picture with 30-meter plus high RCC dams, and the reason why 30 meters, because some countries only keep records of 30-meter plus dams, you can see a very similar pattern. This is clearly shown when you compare the two. From now on, in the rest of the presentation, I will just be talking about 30-meter plus high RCC dams. Now look at the distribution of the RCC dams around the world. 12 countries have over 80% of all the RCC dams in the world. And it can be seen here clearly that China is way ahead of any other country. Over 30% of all the RCC dams have been built in China. It is of interest that if you look at those 12 countries, the 7 which are shown here in bold, China, Brazil, Japan, USA, Mexico, Spain, South Africa, and Australia, were the first 7 countries in the world to build an RCC dam. And they are still in the top 12. If we look at the distribution pictorially, you can see that over 50%, in fact 53.2% of all the RCC dams are built in just 3 countries, China, Turkey and Brazil. And apart from those, the 12 mentioned before, the rest of the world accounts for only 18.6% of all the RCC dams. Looking at the distribution by continent, you can clearly see that the great majority are in Asia, and if you take Asia and South America, it's approaching 75%. We'll now look at the design philosophy of RCC dams. We'll first look at the different approaches to the design of RCC for dams. Then look at the proportion of RCC dams using those different design philosophies. And then we'll look at the average mixture proportions of the different design philosophies. There are 5 approaches to the design of RCC for dams. The first one is for hard-fill dams. Second one is what's known as low cementitious RCC. We then have RCD dams in Japan, which are unique to Japan. And then we have medium cementitious RCC and high cementitious RCC. We'll first look at hard-fill dams. Hard-fill dams are also been called CSG, compacted sand and gravel dams in Japan, and CMD, cemented material dams, in China. And this name has now been adopted by ICOLD, and there is now a separate ICOLD committee dealing with CMD dams. A hard-fill dam has symmetrical with equal or near equal upstream and downstream slopes, generally somewhere between 0.60 to 1 and 1.10 to 1. The volume of the dam is usually significantly greater than traditional gravity dams. The cementitious content is relatively low, or surprisingly, it is in fact over 100 kilograms per cubic meter, 104 kilograms per cubic meter. Requires some form of watertight membrane on the upstream face. No treatment nor bedding mix is required in the horizontal joints because the design does not depend upon any shear strength or tensile strength of those joints. And no vertical contraction joints are required. The first hard-fill dam in the world was a small dam in the southwest of the UK called New Mill. It wasn't called a hard-fill dam, it was just a solution to a number of problems. And there were 3 major problems. The first was that the foundations were very poor and so the load was spread with upstream and downstream slopes of 1 to 1. The second problem was it had to be a concrete dam because it all had to as a spillway, being a flood retention dam, but it is an area of outstanding natural beauty, and the planners did not allow any concrete to be shown. And the third problem was that the concrete had to come from a ready-mix plant, and the travel time from that plant could vary anything from 20 minutes to 2 hours, depending upon the traffic, as the dam was built in a tourist area in the summer. This is the final dam. You can see in the background there's a culvert there which discharges a constant amount of water going downstream at the capacity of the river downstream, and the upstream and downstream slopes have been covered with an earth film covering, and the concept is that most of the water would be retained behind the dam, but if there was a larger flood, it would overtop and run down the downstream face, and in a very severe flood, the fill shoulder on the downstream face would be washed away and the dam would revert to a stepped concrete spillway. Now let's look at low cementitious RCC dams. Generally, they have a gravity section, although the downstream slope can be flatter than usual. The cementitious content is less than 100 kilograms per cubic meter. The SCM, that's the supplementary cementitious materials, content is usually relatively low. It requires some form of watertight membrane on the upstream face. Frequently a full or a partial bedding mix is used on all horizontal joints. Vertical contraction joints are required. Here is a photograph of probably the most typical and the first low cementitious RCC dam, Willow Creek. It's under construction in the USA. You can see from the photograph the RCC was transported by scraper, which is, I think, fairly unique. It was spread by a dozer and then compacted by twin drum vibratory rollers. The total cementitious content was quite low. This is a completed dam, and you can see the water level from the downstream face as the water goes along the horizontal joints, and it is not particularly impermeable. When the dam was first constructed, it was drawn down almost immediately, and a significant amount of money was spent trying to grout the dam. Some people believe successfully. I don't believe that successfully. We'll now look at RCD dams in Japan. These are generally a gravity section, although usually there's an upstream fillet due to the high earthquake loading in Japan. The cementitious content is either 120 kilograms per cubic meter when the height of the dam is less than 90 meters, or 130 kilograms per cubic meter when the height is more than 90 meters. Low-lying fly ash is used as an SCM and is usually 30% of the cementitious content. The RCC is placed in thick horizontal lifts, somewhere between 0.5 and 1 meter thickness. Most popular seems to be 750 millimeters, and 3 layers of RCC are spread for each horizontal lift. There's a thick, usually about 2.5 meters wide width of facing concrete on the upstream face and a 1.5 meter width on the downstream face. All the horizontal joints are green cut and a full bedding mortar applied. And vertical contraction joints are required. They're either formed or induced. This is a photograph of Miyagasi Dam under construction. It's one of the largest RCD dams in Japan is about 150 meters high, and the RCC was transported to the dam surface using a funicular railway, which you can see in the slide. This is the completed dam, and it's a very nice looking dam. If we look at the medium cementitious RCCs now, this is generally a gravity section. The cementitious content is between 100 and 150 kilograms per cubic meter. The SCM content is usually 30 to 40%. Occasionally some form of upstream watertight membrane is used, but usually not. Horizontal joints range from no treatment with hot joints and no bedding mix to a full green cut and a full bedding mix. Vertical contraction joints are required. This is a photograph of Copperfield Dam, which is one of the first, if not the first, medium cementitious RCC dams constructed in Australia. And one particular feature of this dam was that it had an unformed downstream face with no formwork. This is a completed dam, and in the foreground you can clearly see the problems with the unformed face, because it was not possible to form a face at the design slope, and the slope was slightly less, and the downstream face should have been parallel to the top of the training wall, and it was not, and the dam got a little bit thin towards the top. Now let us look at high cementitious RCC. The dams generally have a gravity section, although also used in arch and arch gravity dams. The cementitious contents more than 150 kilograms per cubic meter, and that figure is not grabbed from the sky. It was defined back in the early 1980s, and at that time it was the point at which the impermeability of RCC dams equaled that of traditional concrete gravity dams. Below a cementitious content of 150 kilograms per cubic meter, RCC dams were less impermeable than traditional concrete dams, but above 150, RCC dams can be more impermeable than traditional concrete gravity dams. The SCM content is usually in excess of 50% and can be as high as 75%. No upstream watertight membranes required because, as I mentioned, it's impermeable. Horizontal joints range from no treatment on hot joints to a full green cut on cold joints, and from no bedding mix to an occasional full bedding mix. However, a number of high cementitious RCC dams have been completed with no bedding mixes whatsoever, and vertical contraction joints are required. This is Upper Stillwater Dam, which was the first large high cementitious RCC dam in the world, just under 100 meters high, with a volume just over 1 million cubic meters. It was built in the early 1980s, and the fundamental problem on this site was that the long-term average temperature is 0.5 degrees, and the temperature range is 70 degrees, from -35 in the winter to +35 in the summer. And the construction season was 5 months, give or take a couple of weeks, depending upon the winter. During the summer, when the RCC was placed overnight, because the maximum placing temperature was 10 degrees. And during the day, the faces were formed, and they were formed using an offset slip form paver, and there was no formwork on this particular dam. This is a completed dam, and there are 3 points of interest. First point is the downstream slope is 0.60 to 1, and the RCC has been designed for tensile strength. The second point of interest is no contraction joints were built. Into the dam, and they had what the USBR called was post-form contraction joints, which they hoped to seal. Unfortunately, it was more difficult to seal them, and there have been a problem. The third point is the spillway itself. There is a stepped spillway, and the dam is 90 meters high, and practically all the energy is dissipated on the steps, and you can see the stilling basin is only 9 meters wide. I mentioned there was only a 5-month construction season, and the dam was built over 3 seasons. The RCC was actually placed in 9 months, and there were 2 7-month joints in the dam. This is a core taken 14 years after the dam was finished, and in that core there is a 7-month joint. This is a detail of where the 7-month joint is. This dam had no bedding mix whatsoever. In spite of having no bedding mix and having a 7-month joint, the properties at that joint were exactly the same as the properties of the parent material. In fact, when the testing of the joints here, one could not differentiate between any of the joints and the parent material. This is 2001 when a 1.5 meter long core was taken. 2004, this is a 6 meter long core taken from the Upper Gar Dam. You may think a 6 meter long core is not particularly good, but if you look at the drilling rig which was used, that gentleman there did an extremely good job to get a 6 meter core out in one piece. By 2008, we were taking 10 meter long plus cores as a matter of on a regular basis. This is an 11.3 meter core taken from the Yewa Dam, one of a number. Here's a photograph of one of the 11.3 meter long cores being extracted from that dam. It's in the background is the penstock surround. The same year, a 15.3 meter core was taken from Longtan. Nowadays, if you can't take a 20 meter long core, you failed with the high cementitious RCC dam. This is a dam called Huadang in China, and I took this photograph of 2 cores. One is 20.5 meters long and the other is 24.6 meters long. Now let's look at the proportion of RCC dams using different design philosophies. If we look at the numbers of RCC dams, just under 50% of all the RCC dams for which we know the mixture proportions are high cementitious RCC, but about 18% we do not know. If we take out those unknown dams, we find that 60% of all RCC dams contain high cementitious RCC, 7.5 contain hard fill. Now that figure is a great underestimate because I do not have details of all the hard fill dams, because I've mentioned that they have been taken away from the ICOLD concrete committee and another committee has been set up. Around about 8% are low cementitious, a further 8% RCD, and about twice that medium cementitious. However, this is in terms of number, and what we should be looking at is in terms of volume. Now, if we look at the volume of RCCs being placed, 67% is high cementitious RCC, 8% roughly hard fill, 6% low cementitious, 7% RCD, and about 12% medium. What is interesting is compare these figures with the position in 2000. In 2000, the volume of RCC placed in hard-fill dams was only 0.3% because that's when they basically started out. That's increased to 8.3, as you've seen. Low cementitious has decreased from 10.1% to 5.7%. RCD from 25.7 to 7.1. Medium from 14.4 to 11.9, while high cementitious has increased from 49.5 to 67.0%. At the present moment, the trend is that the high cementitious RCC and the hard fill dams are squeezing out the other form of RCC. Now let's look at the average mixture proportions of the different design philosophies. If we look at the Portland cement content, what is perhaps surprising is the Portland cement content of at least 4 of the 5 are very similar, or between 80 and 87. The low cementitious RCC is slightly lower. What is the big difference between the various forms is the SCM content, where we have with the hard fill and the low cementitious relatively low, 15 to 25, with the medium cementitious and RCD 35 to 40. Meanwhile, with the high cementitious RCC, it's very much higher. It's well over 100 kilograms per cubic meter. Also, perhaps surprisingly, is the water content with the hard fill and the lean RCC, which are very unworkable RCCs. The water content's 120 or slightly above 120. Meanwhile, with the high cementitious RCC, which is far more workable, one would expect, and we are told that the water content is higher, but in fact it's not. It's quite a lot lower. Now this leads to the water cementitious ratios. If you take a low cementitious RCC, the average water cementitious ratio is 1.53, while the average water cementitious ratio of a high cementitious RCC is less than 0.6, less than 40%, which obviously leads to very much better properties. If we now look at the changes in the average mixture proportions of the various forms of RCC from 2000 to 2020, in terms of hard fill, 2000 there were basically no records. But if we look at the other 4 forms, with the the low cementitious RCC, Portland cement content 63, 66, SCM 13, 14, water content 121, 122. Very little change. With the RCD, there's very little change. With the high cementitious, also very little change. The only one which has a change is the medium cementitious, where the Portland cement content has gone up quite dramatically from 63 to 80. And the SCM content's gone down from roughly 57 to 38. And I can offer no explanation for that. Now let us look at the cementitious materials used in RCC dams. If we look at the position, we find just over 50% of RCCs contain Class F fly ash, that's low-lying fly ash. However, I have no records of 22.5%. So if we take out the unknowns, we find that 67.7% of RCCs contain a Class F, that's a low-lying fly ash. Very few contain Class C, that's high-lying fly ash. A little more containing slags, that's granulated blast furnace slag. Combination of SCMs, which was quite popular in the early days, is now reduced to less than 1%. The manufactured pozzolans are a bit more. Natural pozzolan is quite significant now, 16.2%, and no SCMs, in other words, just Portland cement, is a fraction less than 10%. Now, if we look at the changes which have occurred since the year 2000, low-lying fly ash hasn't changed, 67 to 67.7. High-lying fly ash has dropped a bit, 1.2 to 0. Slag has dropped a bit. Combination of SCMs dropped quite a lot. Manufactured SCM roughly the same. Natural pozzolan's gone up, and no SCM, and the Portland cement alone has gone down a fraction. Let us now look at the highest, the largest, and the fastest RCC dams. We'll first look at the highest, then the RCC dams with the greatest RCC volumes, and then the RCC dams with the highest average rates of placement. These are the 10 highest completed RCC dams. The highest is Gibi 3 in Ethiopia. And to get into the top 10, you need a height above 165 meters. And you will notice that 8 of the 10 highest completed RCC dams are in Asia. You'll also notice, as we've seen before, the Portland cement content is in the order of 70 to 100. And there's a big difference in the SCM content ranging from 0 to 120. But 8 of the 10 highest RCC contain a low-lying fly ash. This is a photograph of Gibi 3 in Ethiopia. When the photograph was taken, the water level was about 10 meters from the top water level. If we now look at the RCC dams with the greatest RCC volume, the largest volume is just under 6.5 million cubic meters. And to get into the top 10, you basically need a volume more than 2.5 million cubic meters. Again, 80% of the RCC dams with the largest volume are in Asia. And again, we have the great majority contain a low-lying fly ash, in this case 7 out of the 10. And we have a similar pattern with the mixture proportions. This is a photograph of the largest RCC, Guanyin in China, which has a volume of RCC of approximately 6.5 million cubic meters. Now we look at the RCC dams with the highest average rates of placement. In order to get into the top 10, you need to have an average rate of placement in excess of 85,000 cubic meters a month. Now, I personally find this slide very disappointing, as there are only 7 completed RCC dams in the world which have an average rate of placement in excess of 100,000 cubic meters. The highest is in the stage 1 of Longtan, with an average rate of placement just under 143,000. But notice in the peak month there, 400,000 cubic meters was placed. That's over 1 million tons of material placed in the dam in 1 month. What is different here, whereas in the previous 2 slides, 80% of the dams have been in China, here it's roughly 50-50. 50% are in Asia and 50% are outside Asia. This is a photograph of the completion of stage 1 of the Longtan Dam in China. This project has an installed capacity of 6,300 megawatts. The dam was finished early, and a substantial amount of power was generated ahead of schedule, which generated a significant profit for the project. Now let us look at the speed of construction, which is the most important factor when considering RCC dams and its greatest advantage. This is a plot of the average rate of placement of approximately 700 RCC dams relative to the volume of RCC. The 10 fastest RCC dams have been named on this slide. Now, 98% of all the RCC dams fall within that range shown there. You can see that there are two dams way above that limit, Upper Stillwater and Olivenholme, both of which happen to be in the United States. And you can see on the right 3 dams which are well behind the rate of placement they should have achieved. This is a detail of that figure for volumes up to 2 million cubic meters. And it is clear from this slide that the great majority of RCC dams in terms of the average rate of placement are in the bottom half of that range. And if you look at the top of the range, where, in my view, RCC dams should be, there are very few dams. In fact, one might say that less than 10% of all RCC dams have been constructed as rapidly as they could, indeed should be. One interesting exercise undertook for a relatively small RCC dam, which was roughly 600,000 cubic meters. This is a plot of the average rate of placement of a number of dams of roughly the same size against the total cementitious content. And if one takes a sort of low cementitious RCC with a cement content or cementitious content of roughly 75 kilograms per cubic meter, you can see the average rate of placement was just over 20,000 cubic meters a month. If you then go up to an RCC dam with a total cementitious content of 225 kilograms per cubic meter, the average rate of placement is roughly 40,000. That's double. That doesn't mean to say that just by changing the total cementitious content you can double the rate of placement. But what it does tell you is there is a huge range which a lot of factors will determine. This is a photograph of the overall placement in the spillway half of the Yewa RCC dam in Myanmar. It shows very clearly that it is well designed, if the RCC is well designed and the construction methodology is well organized, the placement of RCC can look very simple. In fact, it's not simple. It needs a lot of factors to be well programmed before and organized. In this photograph, the RCC was being placed roughly at 7,500 cubic meters a day. And you can count up the number of people working on the top of the dam for everything, that is from raising the foam to curing to transporting, dumping, spreading, putting in contraction joints, using the GVR to form the faces, etc. Less than 30 people were working on top of that dam. Less than 30, placing 7,500 cubic meters a day. KISS. Keep it simple. Simplicity is the ultimate sophistication. da Vinci. Amongst everything else, he was probably one of the best engineers that has ever been born. Now let us look at the 4 completed RCC dams in India. We have 3 in Maharashtra, the Gatgar Upper Dam, the Gatgar Lower Dam, Middle Bhatana, and we have 1 in West Bengal, the Teesta Low Dam, stage 4. We'll first look at the Upper Gatgar Dam and the Sattal Dam, then the Lower Gatgar Dam, then Middle Bhatana, and then Teesta Low Dam, stage 4. That is the order in which those 4 dams were completed. Now the Upper Gatgar Dam and the Sattal Dam, which retain the upper reservoir at the Gatgar pump storage scheme. Here's a layout of the scheme. At the top of the photograph, that is the upper dam, and just below it is the Sattal Dam, and at the bottom of the escarpment we have the lower dam. The Sattal Dam was the first one constructed, only 9 meters high, and one could say that was a full-scale trial for the upper dam, which is 15 meters high, which in turn was a full-scale trial for the lower dam, which is 86 meters high. This photograph shows the first RCC placed in the Sattal Dam, and indeed the first RCC placed in a dam in India. And you can see that it's been dumped, and there's absolutely no segregation in that RCC. This is a photograph of the placement in one half of the Sattal Dam. The Sattal Dam was split into 2 halves because it was quite long. This is a photograph showing the overall process. One can see in the background the conveyor which transported the RCC to the dam. Then it was dumped into the trucks. You can see the trucks then dumping the RCC, again with no segregation. Then it was spread and roller compacted. And this is the completed Sattal Dam from the downstream side of Sattal Dam. The water is on the other side, and as you can see, the downstream face is completely dry. This is the dozer spreading the RCC in the left half of the Gatgar Upper Dam. Again, you can see there's no segregation. You can see the dozer is laser guided and has wings on either end of the blade and try to avoid segregation going around the edge of the blade. The upper dam was split into 2 halves of RCC, and in the middle was the spillway, which was constructed of CVC, conventionally vibrated concrete. And the owner took this photograph, that's GOMID, the Government of Maharashtra Irrigation Department, comparing on the left the finish of the RCC, and on the right the finish of the conventional concrete in the spillway. I leave it to your own judgment, but the great majority of people feel the finish on the left, the RCC, is at least equal, if not better, to the finish of the conventional concrete on the right, in spite of the cement content being less than a quarter in the RCC. This is a panorama of the completed Gatgar Upper Dam. Now let us look at the Lower Gatgar Dam. The Lower Gatgar Dam, for the majority of the height of the dam, was split into 2 halves, and we used what was known as split level placement. You can see here the RCC is being transported and being placed in the left half of the dam. This is a schematic showing the process. alternate from the left-hand side to the right-hand side, placing 3.6 meter lifts made up of 12 layers. And when you finish one half, you move over to the other half. Ideally, a swinger should be placed on the joint in between the two, so from one location you can feed both sides. This photograph shows moving equipment from the left side to the right side at the Gatgar Lower Dam using a ramp. This photograph clearly shows one of the main advantages of the spit level placement methodology, because you can see that the RCC is being placed in the far side on the left half of the dam, and at the same time the formwork for the galleries are being erected on the right half of the dam. In other words, the gallery and the installation of the formwork for the gallery actually has no impact at all on the rate of placement. When you reach a certain level and the capacity of the concrete plant is sufficient to place 2 layers per day, you spread from one abutment to the other abutment, full length placement, as it is here. This is a photograph of the completed Gatgar Lower Dam. You can see on the right half of the photograph there is absolutely no seepage whatsoever from the downstream face. This is a photograph I took of a visit to the dam 7 years after completion. And even though I took the photograph myself and I was there, I find it very hard to believe, because the galleries are absolutely bone dry and the walls of the gallery have been painted to suppress the dust. The seepage in this 100% RCC dam, no membrane on the upstream face, 100% RCC, is 0. Now let us look at Middelwartener Dam. Spit level construction was used again, and this is the placement of the RCC in the left half of the dam. The difference between the methodology at Middelwartener compared to Gatgar was that the RCC was transported along a longitudinal conveyor as opposed to coming from the downstream side. At points along the longitudinal conveyor, there was twin loading points which could load trucks. This is the RCC being roller compacted with a single drum vibratory roller. This is GVR, which has been used for the forming of the faces of all the RCC dams in India and the majority of RCC dams now. Ahead of the spreading of the RCC, bunds are formed and grout is placed in those bunds. The RCC is then spread over the top of the bunds, and the GVR is vibrated and the grout is worked up through the RCC to essentially form a vibratable concrete. And this created that excellent finish shown for the upper dam at Gatgar. This is the completed Middelwartener Dam. Again, no seepage on the downstream face. This is a photograph of the gallery. There is a little bit of seepage through one of the contraction joints, but generally speaking, the galleries are dry. This is the last completed RCC dam in India, Teesta Low Dam Stage 4. This shows an overview of the project. In the far distance is the powerhouse. In the middle is the spillway, and you can see the river is being diverted through the spillway when this photograph was taken. And in the foreground is the RCC dam closure section, and the RCC pavements just started in the left half of the closure section. This shows more details of that placement. It can be seen that the RCC comes along a conveyor from the upstream side, is then put into trucks. The trucks, as you can see on the downstream, near the downstream face, dump the concrete, and then it's spread by dozer and compacted by vibratory roller. You can also see the formwork there for the gallery. And here's a close-up of the RCC being placed in the right half of the dam around the gallery. Shafts were used, and this shows the modular formwork to form those shafts. And you can see the surface of the RCC. Essentially, when you walk over the top of an RCC like this, as in this photograph, you should leave a footprint, and the whole RCC should feel like a stiff waterbed, I think is the best description I have heard of the RCC. This is the completed dam with showing the fish paths going up the downstream face. And this is a photograph of the gallery taken 5 years after completion. Again, there's some slight seepage from a contraction joint. Apart from that, the dam is impermeable. Now let us draw a few conclusions from this presentation. There are approximately 1,000 RCC dams in the world that are either complete or under construction. There is therefore a precedent for practically all conditions. A standard RCC dam has emerged over the past decade or so. It is a high cementitious RCC dam, and 2/3 of the volume of all RCC placed in dams to date has been high cementitious RCC. It has a high workability, frequently with heavy retardation, with an initial setting time of somewhere between 18 and 24 hours. And it contains a low-lying fly ash as a supplementary cementitious material. Again, as we have seen, 2/3 of all RCC dams contain low-lying fly ash as an SCM. Obviously, there will be conditions when such a dam is not the optimum, but it should be the starting point for the design of the great majority of RCC dams. The original concept of RCC dams was to provide a simple method of construction with RCC spread horizontally from one abutment to the other. This would lead, and indeed has led, to rapid construction. Unfortunately, some of this simplicity is being lost with some modern RCC dams, and the majority of RCC dams are not being constructed as rapidly as they could and should be. An holistic view needs to be taken during the design and construction of RCC dams, as every aspect of the design and construction impacts on other aspects. It's counterproductive to concentrate on any particular aspect, e.g. aggregate production, and try to find the minimum cost solution for that particular aspect, as it will almost certainly lead to a more expensive and probably slower overall project. Investment spent up front on the investigation of the design and construction of an RCC dam will always, and I repeat, always lead to economic benefits. For example, a very detailed study of the available materials and an extensive trial mix program from Moche Dam in Kenya led to the development of an RCC with a Portland cement content of 35 kilograms per cubic meter. And I repeat that, 35 kilograms per cubic meter, and a fly ash content of 185 kilograms per cubic meter. This is probably the most economic and almost probably the most contractor-friendly RCC ever achieved. Thank you.
Thank you, Dr. Malcolm Dunstan, for the excellent and detailed presentation by sharing the world trends in RCC dam design and construction. I would like to place on record my special thanks to Dr. Malcolm Dunstan for sparing his valuable time and knowledge in today's first virtual lecture. I'm sure all the participants have benefited from his vast knowledge shared during the program. May we proceed further for the question answer session? May I request to the participant for the questions? The participant may ask the questions, please.
यस मैम, आपकी आवाज सब क्लियर आ रही है, लेकिन ये जो ऑडियो आपने सुना है ना, ऑडियो वीडियो, उसमें वॉल्यूम का प्रॉब्लम है। हेलो।
Yes, sir. You are audible.
आपकी आवाज क्लियर आ रही है, लेकिन जो
basis on the
आपने
presentation which you have seen, if you have any questions, you may please ask. Mr. Anil Jain, would you like to ask?
Yes.
Yeah, please, sir.
I would like to know how we place the water stops on the contraction joints which we create on the upstream face in high cementitious RCC dams.
Well, thank you for the question. The water stops and usually a drain behind the water stop are incorporated within the GVR, which forms the upstream face. And so the GVR is normally roughly 500 millimeters thick, and that will then be extended around the water stop drainage system. So it's basically incorporated within the upstream face.
So we do we cut vertical section in GEVR also, or we do not have joint there? You first cut the joint.
Yes,
you first cut the joint, then you place the water stops. Usually in conventional RCC, in conventional concrete dams, we place the water stop simultaneously and we keep on do concreting also. So do we do it same methodology in RCC also?
Yes, you place the water stop and usually the drain behind it ahead of the placement of the GVR, and the GVR is placed around the water stop and around the drain, and then the rest of the contraction joint is cut through the RCC after it's been roller compacted.
Okay.
So you induce the contraction joint by placing some form of former, sometimes a plastic sheet, sometimes a stainless steel sheet, and that is cut into the RCC to form the contraction joint behind the water stop.
Okay. So means in GEVR we place it, we form the joint before placing it, and in rest of the portion we cut the section by either by steel plate or by placing some plastic or anything as you suggested. Am I right?
That's correct.
Thank you very much.
Mr. S. Chaudhary, you have raised your hand. Would you like to ask the questions, please?
Yes, I would like to ask Dr. Dunstan. I have two questions. If my trial mix, I am using fly ash. If the fly ash has the lime reactivity as per standard, but it is not meeting the fineness as per standard, but the mix design is giving the required strength. So can that fly ash be taken for the mix design?
The procedure, when you're looking at combinations of fly ash and Portland cement, is the only way of ascertaining how they actually perform is to use trial mixes. For example, on one particular project, which actually happened to be in India, we looked at a combination of 3 different Portland cements and 3 different fly ashes. And the best combination had a strength which was well over twice the strength of the worst combination. And the different order of performance in terms of the Portland cement and of the fly ash was completely different in each case. So the only way of actually working out what will happen is to use trial mixes. In terms of the alkali content of fly ashes, usually the alkali content is not water soluble, and so it is not usually a problem.
Yeah, thank you. My one more clarification was that the fly ashes I am using for trial mix design, they have got the desired lime reactivity, but sometimes they are failing in the fineness. So if it meets my trial mix design strength, my target strength, then I think it should not be an issue not meeting the fineness.
Well, the fineness usually creates, if you have a coarse fly ash, it will usually increase your water demand. More important than the actual fineness itself is the consistency of the fly ash. As long as the fly ash itself is very consistent, in other words, the fineness doesn't vary, usually you can design around that problem. Now, as I have mentioned quite a few times during the presentation, RCC dams may look simple, but they're not simple. In order to have a successful RCC dam, you've got to get a lot of things right. It's a very linear method of construction, and by that I mean if anything goes wrong, everything goes wrong. You've got to get all these things right, and looking at trial mixes, you have to look at that very carefully and look at a lot of different factors, everything from the setting times to the water demand to the variability of materials to which material works with which other material, etc., etc. But the most important thing with your materials is to have them consistent. As long as they're consistent, you can normally design around them. What is much more difficult is to design an RCC in which your materials are variable.
Okay, thank you. And one more question I have, whether have you done any RCC trial mix design, or have you used limestone dust in a RCC mix?
Yes. For a dam called a dam in Spain, yes, limestone dust was used.
Can limestone dust replace fly ash?
There is no answer to that. It depends upon your materials and depends on a number of other factors. As I said, with all these things, there are so many variables. You have to know what you're doing with those variables, but it has been done before.
Okay, thank you for your clarifications. I quite appreciate that.
Do we have more questions?
I have one more question.
Please.
For these vertical shafts or horizontal tunnels, do we use prefabricated RCC panels, or we make cast in situ also?
Both solutions have been used. I personally prefer cast in place, and the reason for that is that when you come to inspect a dam in 10, 20, 30, 40 years' time, if you have cast in place, you can actually see the RCC, because generally speaking, we use GVR around the galleries. If you have a precast gallery, you're not able to inspect the concrete because, of course, all you can see is the precast concrete. But both solutions have been used, but I personally prefer to use cast in place.
Thank you.
Now I request to the participant, if they have any further questions, they may write directly to the organizers EBIP. We will get back to you over your individual emails after getting the answers from the speakers. Thank you, Dr. Malcolm Dunstan, for sparing your valuable time. Thank you, sir. Now we move further for the second presentation. Yeah, please. Now we move further for the second presentation. Now we invite second resource speaker, Dr. Quentin Shah, to make a presentation on Introduction to ICOL Bulletin 177. Let me introduce briefly about the speaker. Dr. Quentin is a consulting dam engineer specializing in the design, analysis, materials, construction, and safety of concrete and RCC dams. Additionally, he has extensive experience in all dam types. He is currently serving his second term as chairman of SANCOL. He is vice chairman of ICOL's Committee on Concrete Dams and was the lead author for ICOL Bulletin 177 on RCC dams. During his 37 years career, Dr. Quentin has worked on more than 150 dams in 34 countries, the highest being the 275-meter Yusuf Ali double curvature concrete arch dam completed in Turkey in 2021, for which he was the chief design engineer. He has worked as an RCC specialist on 18 projects to date, being responsible for more than 9 million cubic meter of RCC. Dr. Quentin has acted as a specialist and panel of experts member on numerous large international projects. Dr. Quentin has published extensively and has been a keynote speaker and invited presenter at several international symposia. In July 2018, he received the ICOL Innovation Award for his groundbreaking work on the early thermomechanical behavior on RCC in large dams. He is a fellow of the Institution of Civil Engineering UK and a fellow of the South African Academy of Engineering. Now I invite Dr. Quentin Shah for making the presentation. Over to you, sir. Would you like us to play the presentation on your behalf, or you would be playing on your own, sir?
Yes, good morning, everybody. If you can play the presentation, I think that would be easiest and safest.
Sure, sir. May I request my IT team kindly play the presentation, please?
Just give me a minute, ma'am. I will run it from here.
Sure.
if I can just say, perhaps while the presentation is loading, that this first presentation is essentially on the ICOLD Bulletin 177 on RCC dams that was published in 2018 and in its final English and French form in 2020. So it really is the latest document on latest RCC technology, and realistically forms the basis of this series of presentations in this workshop. So basically, the individuals presenting were the authors of the particular chapters of this bulletin. Thank you. Okay, so you need to click on, please, from this slide. The presentation runs automatically after this slide. Okay, that's not encouraging. The soundtrack doesn't seem to be there. So maybe I must talk to this then. So this introduction to ICOLD Bulletin 177. So we'll start with a look at the history of ICOLD RCC bulletins, discuss about Bulletin 126, talk about motivation for the update of 126, changes in terminology included in the new bulletin, key developments in RCC, still don't have the soundtrack. So we'll talk about key developments in RCC dam technology, talk about hard fill, and then talk about the workshop presentations. Next slide, please. So the first ICOLD bulletin on RCC dam was published in 1989. It was bulletin number 75. If you can click down the slide, please. So the bulletin presented a review of the first generation of RCC dams, illustrating the state of the art at the time in what was recognized as a technology that was very much in an evolutionary phase. And the bulletin documented practices and approaches in various countries, and particularly avoided recommendations and actual guidance. So this bulletin so with the technology changing and developing rapidly at the time, a second RCC bulletin was initiated in around 1993, attempting to consolidate the state of the art and provide greater guidance in best practice in RCC. And after a difficult process of publication, of compilation, this bulletin was finally published in 2003 as ICOLD Bulletin number 126. And this bulletin particularly differentiated between two approaches for RCC dam design, being the overall and the separate approach, with impermeability created in the RCC itself for the overall approach, and a reliance on a separate impermeable barrier in the case of the separate approach. So the particular relevance and importance of Bulletin 126 can be seen in the facts that the bulletin had the highest print numbers of any ICOL bulletin until that point in time, and was translated into more languages than any other ICOL bulletin to that point in time. So this was a very important bulletin for ICOL and a very important bulletin for the dam design and building industry. So it's undoubtedly true to say that Bulletin 126 provided a great deal of very useful guidance for a particularly prolific stage of RCC dam construction. So if you remember from Dr. Malcolm Dunstan's presentation, there was a very steep curve of RCC dam development, very sort of around and after the period that this bulletin was produced, and it was undoubtedly very instrumental in that period of RCC dam development. Next slide, please. So Bulletin 126 put forward several new ideas and concepts, but for which little experience in terms of practical application existed at the time. It really sort of modernized, in terms of concept, modernized what had been done up until that time. And if you can give me the next click, please. And since then, many of those concepts, so by the time that a new or an update of the bulletin was considered, many of the concepts were much better defined than in Bulletin 126. And basically, additionally, Bulletin 126 essentially represented industry practice of something like 15 years previously. And so it was clear that it should be time to update the bulletin, and particularly in that intervening period, it could be said very definitively that RCC had replaced conventional mass concrete as the conventional material and method for the construction of gravity dams. So considering the fact that RCC is a particularly important dams technology, and the fact that ICOL bulletins must represent the state-of-the-art practice, and the fact that the success of RCC dam construction is not often achieved, as stated by Dr. Malcolm Dunstan, and the bulletin is an important document in enabling the success of an RCC dam, the implementation of an RCC dam, it was decided to prepare an update of Bulletin 126. And while the basic framework of Bulletin 126 was retained, as the new bulletin preparation advanced, it became obvious that changes compared to the Bulletin 126 were actually quite extensive, and Bulletin 177 was subsequently presented as a full new ICOL bulletin. Next slide, please. Just to talk about some changes in terminology that were made in 177 compared to 126. So the term supplementary cementitious material, SCM, was used in preference to pozzolan. And very important changes in the definition of paste are now made. So we used to talk of high paste and lean RCCs. And when we were talking about that paste, we were talking about cementitious paste, which is cement, supplementary cementitious materials, chemical additives, water, and entrained air. Now we differentiate between total paste, cementitious paste, and total paste, where total paste is the cementitious paste plus the non-cementitious or non-plastic fine. So the material less than 75 microns in the mix. So as I mentioned, because of the above changes, the concept of high-paced and lean RCC is no longer relevant, although it does creep in occasionally, with many different levels of cementitious materials content being now associated with a high total pace content RCC. Next slide, please. So for clarity and consistency, the terms lean RCC and high-paced RCC are consequently no longer to be used, with the following being adopted. So basically LC RCC, so this is below cementitious RCC, using the same definition of a total cementitious materials content of less than 100 kilograms a cubic meter. Then we have MC RCC for medium cementitious RCC between 100 and 150 kilograms a cubic meter, and the high HCRCC, high cementitious RCC, with a total cementitious materials content of above 150 kilograms a cubic meter. Next slide, please. So a key requirement for the new bulletin was to also include various recent developments in technology, which include, and I will just mention these in this presentation, as these will be covered in detail in the following presentations to be made. So developments in the understanding of the early behavior of RCC, design differences in RCC compared to conventional mass concrete dams that relate to horizontal rather than vertical construction, developments in RCC mixed design, developments in RCC construction techniques and technologies, developments in RCC arch dams, and developments arising from the use of RCC in more extreme environments. Next slide, please. So Bulletin 126 contained a section, a chapter on hard fill. And as Malcolm Dunstan mentioned, this has been now separated under a separate committee, ICOL committee, and termed the cemented materials dams. But nevertheless, it is a form of roller compacted concrete and really does have relevance in the overall scope of roller compacted concrete dams. There is a very large overlap, even though it is now covered by two different committees. Next slide, please. So for the in-cold workshop, the presentations have been structured as follows. We heard first from Dr. Malcolm Dunstan on the world trends in RCC. We will hear shortly a presentation on RCC dam design. Subsequently, we will look at RCC dam rehabilitation and raising, which will be presented by Michael Rogers. We'll then look at RCC materials and mixed proportioning, which will be presented by Francisco Ortega. Subsequently, RCC dam construction, presented by Rafael Ibanez de Aldecoa. Following that, we'll look at RCC quality control, presented by Dr. Marco Conrad. Then the seventh presentation will be RCC dam performance, prepared and presented by Timothy Dolan. And then we'll look at RCC construction systems and automation, which will be presented by Chris Hicks. And that basically ends the introduction to Bulletin 177. The presentations to be made as part of this workshop will actually be the most comprehensive presentation related to Bulletin 177 yet made. And I think there will be certain parts of these presentations that will actually go slightly beyond Bulletin 177. So this INCOLD workshop is quite fortunate in realistically being receiving a presentation that is absolute current state of the art in roller compacted concrete dams. Thank you very much. I'm happy to
Thank you,
take
sir. Yes, please. Thank you, sir, for your presentation on introduction to ICOL Bulletin 177. Do we have the question related to this session, or should we close this for the lunch break? Mr. Anil Jain, would you like to ask? You have raised your hand. Do we have any questions? Or as informed earlier, the participant may write directly to the organizer, CBIP, or we will arrange their respective answers with respective resource speakers and revert back to you individually over your email. Thank you all for your time. See you all after the lunch break at 1500 hours IST.